Hello again, welcome back. In this video, we're going to work on two important examples in which we apply Gauss's law. The first example we're going to consider is an infinite line of charge. And I want you to recall what we mean by infinite. Oftentimes, engineers will approximate things to make their lives a little bit simpler. We can approximate a line of charge as being infinite when the line is longer than other relevant dimensions. What we're going to do is take this line and place it on the z-axis. So here's x, here's y, here's z, and here is the line of charge. Now I can't obviously draw an infinite line of charge, so I'll just draw those little squiggles up there, meaning it continues on. So suppose this infinite line of charge has a uniform charge density rho L. And recall that we solved this problem where we found the electric field due to this line of charge. We used Coulomb's law along with integration to show that the electric field due to this thing was rho L over 2 pi epsilon 0 rho in the rho direction. Rho here, so we did this in cylindrical coordinates. Rho here is the distance away you are from the z-axis, or the line of charge. Now, if we are to find the electric flux density at point P, so remember that the electric flux density D and the electric field are related. They're proportional and they're in the same direction. So to use Gauss's law, we're going to use the electric flux density, but we can then easily get the electric field. Let's say we have a point P. Right? If we're going to find the electric flux density at point P, we're going to choose a surface that is a cylinder passing through point P, because we have to compute, for Gauss's law, a closed surface integral. So what surface is that? Well, we get to choose it. So we're going to choose a cylinder that passes through point P, and we know from symmetry that the electric flux density is normal to this surface and constant at the surface. And so this would make a Gaussian surface, is what we would call this. So let's just draw it first. So the cylinder passes through point P. Here's my cylinder. Notice two things. D, why did I choose a cylinder for a Gaussian surface? D will be normal to the surface. Okay, except for the top and bottom, which I'll talk about in a second. But other than that, D is normal to the surface. How do I know that? Because the surface is a cylinder, it's curved, and normal to the cylinder then is in the rho direction. Well, D is in the rho direction because E is in the rho direction. So from symmetry. Also, D is constant everywhere on the surface. How do I know that? Well, again, from symmetry, we have an idea of how the electric field works, and it's going to depend on the distance I am away from the line of charge. Well, by definition, a cylinder, or the outer edge of a cylinder, is the same distance away everywhere on the edge from the axis. These two things together make a good Gaussian surface. surface. Okay, we would call that a Gaussian surface. Now let's get to the mathematics. Gauss's law in integral form says that the closed surface integral of d dot ds, S is the surface of my Gaussian, or my Gaussian surface, is equal to the charge that's enclosed by that surface. Okay, well, how much charge is that thing enclosing? Well, I've got a charge density of the line that's in coulombs per meter. So then if I multiply by the length of the line, that's in coulombs now. So that's the amount of charge this thing is enclosing, this Gaussian surface. Now, D only has a rho component, as we already talked about. So we can write D as being that rho component in the rho direction, like this. Now, putting those two pieces together, I've got this. Through the surface really has the curved side, like the label on a can of soup, and then the top and the bottom. So really now, I'll represent that like this. We'll say curved. Actually, this is not closed anymore. Then this is curved surface dotted with. We'll call this S1 for the curved surface, and then plus, and I'll say top bottom. So this is the top and the bottom, dotted with, we'll call the top and the bottom S2 is equal to rho L times L. So together, the curved surface and the top and the bottom make a closed surface. And the reason I'm writing it like that is because the flux through the top and the bottom is 0, because in this case, a normal to the top is in the z direction, and normal to the bottom is in the minus z direction. And so rho and ds are perpendicular for the top and bottom, and the dot product then is 0. So that leaves just the curved surface. Now, as we said, everywhere on that curved surface, d is a constant. So we can bring the d rho out, and then I have this, and because they're normal, that is the a rho, the direction of d, and to the surface, so that is to say that a rho and ds1 are parallel, because ds is also normal to the surface. Then the dot product of those two vectors, this should be a vector, is 1. The dot product is 1. So now I just have ds like that. Excuse me, the dot product of those two vectors, unit vectors, would be 1, and then I have ds. Alright, now, when you integrate over the curved surface, then you just get the area of that curved surface. So what is that? Well, the circumference of that can, if you want to think of it, the cylinder, is 2 pi rho, and then the length is L. So that's the area of that surface, like that. And so then we can solve for d rho, of course. D rho is just, notice the L's drop out. as they should, because we're saying that this thing is infinite long, so we don't even have a good number for L. And then this would imply then that the electric flux density is rho L over 2 pi rho times a unit vector in the rho direction. And recall that D, we defined it as epsilon 0 times E. So that would make E, the electric field, which is usually what we want, is 2 pi epsilon rho in the rho direction, like that. That's the electric field. And lo and behold, that matches what we did for Coulomb's law. Nice. All right, we're going to go to another example now. This is going to be an infinite sheet of charge. And I'm going to draw the sheet here again in the xy plane. So I've got an infinite sheet. Let's see. Again, just kind of show the breaks there. But this thing is lying in the xy plane, and it's got some charge. So suppose that it's in the xy plane and it has a charge density of rho s now because it's a surface. Using Coulomb's law and integration, we showed that the electric field due to this infinite charged, not infinite charged, infinite sized sheet is rho s over 2 epsilon 0 times a unit vector in the z direction. Now, if we're going to find the electric flux density at point P, maybe this is point P up here, we're going to choose a surface again that needs to be constant at point P, or on the surface, and that needs to be normal to the electric flux density. So we are going to choose a rectangular prism. I'll draw that in blue. Our surface is going to be a rectangular prism like this, that cuts through the plane there, the sheet that contains point P on the surface. So from symmetry, the electric flux density is normal to this surface on the top and bottom. So why is that? Well, remember the electric field due to this thing, was going like this. It's going like this. So on the top and bottom, the electric field or the electric flux density is normal to the surface, which means it's parallel to the surface vector. And then it's tangential to the sides, so that's going to be useful. And the flux density is constant at the side with P. Thus the prism is going to make a good Gaussian surface. That's our Gaussian surface in blue. All right, let's get to the mathematics. So I'm going to compute a closed surface integral of d dot ds. The surface is the blue thing, S. And according to Gauss's law, that's equal to the charge enclosed by my surface. Now, how much is that? Well, let's say that our surface has an area, cross-sectional area of A. Then the amount of charge that this thing is enclosing is the surface density, right, which is in coulombs per square meter, times the area of the sheet that this thing cuts off. Now, the left side, d dot ds, is equal to the top d dot ds plus the bottom d dot ds plus the four sides d dot ds, and so that must be rho s times a. So all I did was I converted this closed surface integral into its 6 constituents, and I put the four sides together in one. And the reason I did that is we know that d only has a component in the z direction as I've drawn e. Remember, d and e are parallel with one another. So we can write d as some component in the z direction times a unit vector in the z direction. So now my integral becomes over the top dz ds, like this. Again, s on the top, s also points in the z direction. So they're parallel. So when you do the dot product of two unit vectors, you get 1. Two parallel unit vectors, you get 1. And so then all we have remaining there is dz and ds plus the bottom, and by the same argument, we got dz ds of the bottom. Maybe I should call that 1 and 2, but they have the same area, the top and the bottom, so we'll just leave it as ds plus 0. And this is 0 because the sides have surface vectors. I'll draw this in purple. The side on the right points to the right, the side on the left points to the left, and the side in front of us comes out towards us, and the side in back of us points away from us. And so in each case of those four sides, the surface vector is perpendicular to E and D. And so when you do the dot product, you get 0. Right? That's the point of using such a surface, such a Gaussian surface. So now the dz's can come out because they're constant at the top and at the bottom, because I'm the same distance away from the sheet. Everywhere on the top face is the same distance away from the sheet, and everywhere on the bottom face is the same distance away from the sheet. So that would be a constant electric field, a constant flux density. So now I've got dz coming out times the integral over the top ds plus, again, dz coming out times the integral of the bottom ds equals rho s times a. So when I integrate, a constant over ds, then I get just the area. So I get area A, and I get another area A equals rho s a, like this. And so what we find is that, notice first of all, the a's cancel, and I get the z component of the electric flux density is rho s over 2. And so that if that's the z component, and we only have z component due to symmetry, then the electric flux density vector is rho s over 2 times a unit vector in the z direction. Bam! And what about that electric field? Well, remember that the electric flux density was epsilon 0 times the electric field. So this would make the electric field rho s over twice epsilon 0 in the z direction. Bam! And also, I'm going to draw an exclamation point because that matches what we did with Coulomb's law right there. All right. So those were two important applications to Gauss's law. And I've got another one coming up in the next video. So I'll see you there. Stay tuned.